So in this video we're going to be going over the concept of partial fraction decomposition, which is the tool that we'll be using to integrate in the next homework assignment. So here's the basic idea. The idea is, suppose that you started with a sum of two ratios. Let's say you were adding 4/5 plus 2/7. Well, one way that you can add these two fractions is to identify that a simple way of getting a common denominator is just to take the product of the two denominators that you have to begin with. So I could just go 5 times 7. And if I did this, I would actually, to get the numerators, I would actually need to do 7 times 4, which is 28, plus 5 times 2, which is 10, which is the same thing I would get if I multiplied by 7 over 7. 7 times 4 is 28, and by 5 over 5, where 2 times 5 is 10. So kind of a shortcut for brute force common denominatoring is take the product of the denominators, and then numerator times denominator plus numerator times denominator, and you add your numerators up and you get 38 over 35. And so you wind up in the end with a single ratio. We took the sum of two ratios and wound up with the sum of a single ratio. Well, what you could do is ask yourself, what would happen if you were trying to work in the opposite direction? What if you didn't see where 38/35 came from? What if you started with 38/35 and you wanted to know if it was the sum of two or more ratios? Well, a strategy that you could employ to determine this would be to factor the denominator that you have, the 35, into its factors, 5 times 7, and then you could identify that these are the candidates for denominators in ratios that you add up to get 38/35. And you could say, hey, I wonder what goes here, and I wonder what goes here. And then you'd have to come up with some techniques for figuring out what A and B actually are. So this is kind of the key idea that's going to be used in partial fraction decomposition. So instead of starting with a ratio of integers like I did here, you start with the ratio of two polynomials, a polynomial in the numerator. So the number 1 is a degree 0 polynomial, and here's a degree 2 polynomial in the denominator. And what you do is you identify that x squared minus 5x plus 6 maybe came from taking the sum of two other ratios of polynomials. And the question would be, how do you figure out what these two ratios are? But the strategy would be the same as it is when you're working with integers like we did up here. You would take and look at the factorization of the denominator to get your possible denominator. So for example, x squared minus 5x plus 6 can be factored as x minus 3 times x minus 2. So these two factors then become the candidates for the denominators in the two ratios that we add up to get this single ratio. And then our job is to figure out what goes in the numerator. And so it turns, and the idea here is that we may be trying to integrate something like this, and we may find that the ratio of polynomials is difficult to integrate. In this particular case, we would have to complete the square on the denominator and then use trigonometric substitution to evaluate this integral. But it might be the case that if you can decompose, that's why it's partial fraction decomposition, take a single ratio and decompose it into the sum of two or more ratios. What if it turns out that the individual ratios are easier to integrate than the ratio that you started with? And this is the idea behind partial fraction decomposition. Take a ratio of polynomials, figure out how the denominator factorizes, and then come up with a set of guidelines for figuring out what the numerators need to be, and then look at the resulting sum that you get and see if the individual ratios are easier to integrate than the original ratio. So the next slide, there's a set of guidelines that we follow for doing this. This isn't a comprehensive set of guidelines, so the first thing to realize is that guideline number 4 is for a second degree polynomial in the denominator being raised to the nth power. We could add a guideline number 5 for a third degree polynomial being raised to the nth power, all the way through guideline n, which would be for an nth degree polynomial being raised to the nth power. So that's the first thing to realize. This isn't a comprehensive list of guidelines, but it is enough of a list of guidelines to where if we had some higher degree polynomial in the denominator, we should be able to establish what's going on here and then come up with our own guideline for that nth degree polynomial. That's the first thing I would say. The second thing I would say is each of these guidelines make a lot of sense, and what I would encourage people to do is look through and think about what the guidelines are saying and why they are written the way that they are. See if you can figure out on your own why these make sense. And if you're a math major in particular, this should be something that you try to do. Here's this list of guidelines. So we can take two approaches to a list of guidelines like this. We can just use it and get the right answer in the homework, or we can do what a mathematician ought to do and try to make sense of the guidelines and why they work the way that they do. So you should pause the video, copy these into your notes. These will be the guidelines that you use to work your way through the next homework assignment. In the videos that come next, I'll be working through examples of applying these guidelines to resolve integrals.